So, Chapter 4 of Cisco 2 is kind of partially a review of switched networks and then some Cisco terminology, borderline marketing material on how Cisco does switched networks. So, let's take a look. So, first part is looking at LAN design, explain how switched networks can support small to medium-sized businesses, explain how the data and voice are converged, and just going through this stuff. Then we're going to review how switches work and how switches do switching. And some of this is a direct review of Cisco 1. So if I come in here and look at LAN design, so networks need to be, I don't know about next generation, but yes, they do need to be secure, reliable, and highly available. And they must be able to integrate into your older devices as well. Convergence. That's where we're carrying telephone, data, and video over one network. Traditionally, before this, instead of voice over IP, we had two copper wires to carry a voice communication. Data was carried over Ethernet, and video was carried over coaxial cable. So you actually had three different sets of wire in your building. Now everything is just data being sent over IP packets, most likely on an Ethernet network. So now we get into one of the slides in this chapter that I think is more marketing material than specifically about switched networks, and they go in talking about Cisco borderless networks and all the wonderful features they have where they can allow organizations to connect anyone, anywhere, anytime on any device securely, reliable, and seamlessly. Sounds like market speak to me. Gives us a framework to unified wired and wireless access and provides network services, user endpoint services, blah, blah, blah. So the main thing that they start talking about, and the terminology you need to know for this chapter test, is the core layer, the distribution layer, and the access layer. So this is hierarchical, which means each layer has its own job. It's modular, so it allows seamless expansion and integration. Resiliency provides always available networks. Like if you notice, this switch is connected to two different parts of the distribution layer. So if this goes down, or if this one goes down, we're still up and running. This switch is connected to both. This switch is connected to both. So we have that resiliency in case we have a single point of failure. So the core layer is carrying the heavy traffic, has the heavy bandwidth connections. The distribution layer is connected up to I'll call them the endpoint switches, the endpoint devices that actually connect to the end devices. The phones and the computers and TV for video and all these end devices, laptops and computers. And one little interesting tidbit here is the voice over IP phone is actually a also a little switch, so you can run the network cable from your PC in your office to the phone, and then the phone acts as a switch for that, and then the phone has a connection to the network, so you only have one connection per office instead of two. Now you can do it either way. If you're wiring a new building, you're probably putting multiple network connections in each office or each cubicle. But if you're retrofitting, it's an older building, it's expensive to run multiple cables throughout the building. It's less expensive to do it when the building is built. So you may have it this way. So we do need to know these three tiers in the hierarchical model: the access layer, which is what the end devices are connecting to; the distribution layer, which is letting these endpoint access layer switches and Wi-Fi access points connect to the distribution layer; And then the core layer that's doing the heavy movement of the data. And of course, you can see at the core layer, we have firewalls and multiple router firewalls to connect to the internet. And we have multiple connections to the internet for redundancy and multiple paths to the internet through more than one router. So the access layer is pretty straightforward. It provides network access to the user. The distribution layer sits between the core layer and the access layer. So it's an interface between the access layer and the core layer. So it aggregates layer 2 broadcast domains and layer 3 routing boundaries. It provides intelligent switching, routing, and network access policy functions to access the rest of the network. And then the core layer is your network backbone. That has your high speed 10 gigabit fiber optic links, etc., etc. Smaller networks, we can take the distribution layer and the core layer and collapse them together. And that's what they're showing right here. And you can see that on figures 1 and 2. So there are some drag and drops here. This activity, part 1 on button 1 is pretty straightforward. Activity part 2, identify switched network layer functions. You will have to do this multiple times to get a good feel for which is the core layer, which is the distribution layer, and which is the access layer. So I recommend you do this. You hit reset, you do it again, you hit reset, you do it again. Do this at least 5 or 6 times. This one's pretty straightforward, number 1. So make sure you do those activities. So Cisco says that this model of the core, the distribution, and the access layer gives you more flexibility, more quality of service, additional security. We have at the distribution layer, we have layer 3 switches. So this is primarily a switch, but it is also a router. It can do routing decisions based on IP addresses and networks, but it's also doing switching based on MAC addresses versus down here, we're just switching. We're just doing layer 2 frames, not layer 3 packets. And it gives us that flexibility. And here's our high-speed links with redundancy. So this slide, Cisco's talking about the different form factor of their switches. You have fixed configurations where the number of ports is whatever it is you bought forever and ever. You have modular configurations where you can basically plug in cards to add more ports or different types of ports. You also have stackable switches where you're plugging a high-speed connection from one to the other. And then you have considerations when selecting the switches: cost, port density. This slide, there's 4 buttons on the curriculum on this, and this slide doesn't really explain them all. Let me jump out to the curriculum. So as far as the considerations when selecting a switch, you have more verbiage here describing cost, port density, power than the slide has, the PowerPoint slide. Here are your fixed configuration switches, which it talks about in the curriculum right here. Here are your modular switches, which it talks about in the curriculum right here. And then here are your stackables. So this one, you're much better to make sure you read through these 4 buttons carefully on the curriculum. And then finally, 4123 is a drag and drop asking you about button number 1, the cost, the port density, etc., etc. So go through this a couple times until you feel comfortable with it. And that is the next slide in the PowerPoint. So section 4.2 is mostly a review from Cisco 1. So let's take a look at it. Let's look at how a switch decides to forward frames. First of all, remember that switches work with frames. That's layer 2, and that's MAC addresses. Layer 3 is packets, and that's IP addresses. Switches make their forwarding decisions, what port to send a frame to, based on the MAC address. So in this example right here, they have abbreviated the MAC addresses to 2 digits. Normally, they're 48 bits long, okay, 12 hexadecimal digits. So in this case, there is a device that is on port 1 with the MAC address of EE. And when it sends the frame to the the switch looks at the destination MAC address field of the frame, sees that the destination is EA, it looks through the port table, the MAC address table, and discovers that port 4 is where EA lives, so this frame is going to get sent out port number 4. And you'll see that if you watch the animation. Now, remember, the port table, the MAC address table, gets built by looking at the source MAC address of each frame as it comes into the switch. So the first time a frame comes into port 1 with a source address of EE, it fills out the port table. The first time a frame comes into port 4 with a source address of EA, it now knows that EA is on port 4 and AB is on port 6. So it takes it a little while to build up this port table based on traffic. If a frame comes into port 1 and it has a destination address, a destination MAC address that is not in the port table, it will send it out every single port except for the one it came in. So it will send it out ports 2 through 6. Now, if the destination address is all ones, all 48 bits are 1, that's a broadcast, and then it will also send it out ports 2 through 6. And there's some other cases like multicast that will send it out all available ports except for the one it came in on. Now, 4212 is about a 3-minute, if you want to get exact, 3 minutes and 9 seconds. I checked video reviewing how switches build the MAC address table and how they decide where to send frames. So please watch that and make sure you understand it. All right, so when switches receive frames, they can forward the frames a couple of different ways. The first way, and probably the most common, is store and forward. The second way is cut through, and there is a third way that we'll talk about. I think it's on the next slide. But remember that a frame in the trailer of the frame has a frame check sequence. So when the frame is built, whatever device is building that frame looks at all the data in the frame, all the fields of the frame, and does a mathematical calculation on it and comes up with a number. The exact way the CRC is done, the cyclic redundancy check is done, is unimportant. But it does that calculation, stores that number in the trailer. Okay, when the frame comes into the next device, the next switch, that switch independently does that calculation to come up with the CRC and compares it to what is in the trailer of the frame. If the two match, it's a good frame, and it will forward it out of the switch to its destination. If they do not check, if they get different numbers, that is a CRC error, and it will discard the frame. Now, that adds some latency, some delay, because you have to receive the entire frame before you can send it out. So there is another method called cut through, and that means as soon as just enough of the frame has come in to get the destination address, then even as the frame is coming in on the source, it starts sending it out to the destination. And then after that's all done, it will do the CRC check and see if it received a bad frame. If you get too many bad frames, the switch will switch over to store and forward. Well, you can watch these animations on figures 1 and 2 on 4213 of the curriculum. So if you're looking at a frame, okay, the frame header has an 8-byte preamble, a 6-byte destination MAC address. So as soon as this much of the frame has come in, it can look at the destination MAC address on cut through and start sending the frame out. So then you notice the very next field is the source MAC address, and this is what the switch uses to build the switching table. Okay, then we have the type, which talks about what's the data. Here's the network header, this is the packet header, that's the segment header, and here's the data. Here's the data of the packet. And then in the trailer is the frame check sequence. So the error checking after receiving the entire frame with store and forward it compares the frame check sequence, that CRC value, in the last field against its own independent calculation, and only frames that do not have errors are sent out. Automatic buffering. The frames are automatically buffered in the RAM of the switch, and that's what Cisco switches do by default. Okay, this is cut through. Rapid frame forwarding. The switch can be made to make forwarding decisions as soon as it has looked up the destination MAC address. So as soon as it has received the first 14 bytes, 8 plus 16 is 14, it has the destination MAC address, and it can decide where to send that frame and be sending the first part of the frame out as it is receiving the rest of the frame. It can send it out immediately. Now, fragment free is a modification of cut through, rapid frame forwarding, where it receives the first 64 bytes of the frame to make sure the frame is at least the minimum allowable length. Frames are not allowed to be less than 64 bytes. And if it gets at least 64 bytes, then it can start sending it out. And that just avoids, with cut through, you can send out a runt frame that is obviously corrupt, because if the frame is less than 64 bytes, it will not be a valid frame. So this is kind of a compromise, and it has a little bit of error checking than cut through, and it increases the latency a little bit because you have to wait to get the first 64 bytes instead of the first 14 bytes. Now, I will mention one more thing about this 64 bytes. If you look online at the minimum frame size, it will sometimes be referred to as 64 bytes, and it will sometimes be referred to as 72 bytes. They are both correct, because the websites that say it's 64 bytes do not count the 8-byte preamble. The ones that say it's 72 bytes say 64, which is the rest of the frame, plus the 8-byte preamble, that's 72. So both answers are kind of correct, but it is something that can be confusing. So do this drag and drop activity. It's pretty straightforward, and you can check off which attributes are store and forward and which are cut through. I think the only one that is a little bit confusing is when it says the destination network interface card discards any incomplete frames. This is cut through, because if you were doing store and forward, the destination network card would never get the frame. So go through this at least once or twice till you feel comfortable with that activity. Now, this is a direct repeat of Cisco 1 activity, switch it, and this is to make sure you understand how the switching table is built and used on a switch, a layer 2 switch. So I'm going to jump out to the curriculum here just for a minute, and we'll do a few of these on the lecture video. All right, so now I am on 4217, and I have a frame that has come into the switch. It has come in on port number 3. The destination MAC address is 0E, and if I look at my MAC table, 0E is port 9. So this frame is going to be sent out port 9. Now the next question is the source MAC address in the switching table? So 0B is already in the switching table, so it will not add it. So this is going to be a unicast frame. It's not a broadcast. The destination is not FF. And it is not going to add the source MAC address to the MAC table because it's already there. Correct. All right, let's get a new problem. So in this problem, the destination MAC address is 0D. The source MAC address is 0F. So let's look at the source MAC address. Is the source MAC address in the switching table? No, it's not. So 0F is on port 9. So the switch is going to add 0F to port 9. And you can have multiple MAC addresses associated with one port, because you could have a switch plugged into another switch, or in this case they have a hub with 2 devices on it. So there can be tons of MAC addresses associated with one port. 0E is already in the MAC table for port 9, but now it's going to add 0F. Now let's look at the destination address. 0D is not in the MAC table, so it's going to send it out to all ports, all connected ports, except for the one it came in on. So port 1 is connected. Port 2, there's nothing plugged into, so it's not going to send it there. 3, 5, and 7. So it's going to send it out to all these ports because it does not know where to send it. Check. Incorrect. What did I do wrong? Oh, I forgot to check. Frame is a unicast frame and will be spent. Frame is a unicast frame, but it's going to be flooded to all ports. Check. Now it's correct. So what I said was correct. I just forgot to check that off. So let me do one more new problem, but I'm going to keep going with the problems until I find a destination MAC address of FF. So this is a broadcast. First thing the switch does, well, not the first thing, but the first thing I'm going to look at is 0F in the switching table. It is. It's already on port 9. That's where this frame is coming in. Destination MAC address is FF, so it's going to send it to all the ports except for the one it came from. So that's going to be 1, 3, 5, and 7. And that is a broadcast frame that will be flooded to all ports, all connected ports. And correct. So make sure you do switch it enough times that you're getting them all correct and you understand how items are added to the switching table and how it decides where to send them out. Very good exercise. It's a repeat from Cisco 1. All right, another situation that you will probably never run into, but you need to understand, is the concept of collision domains. So collision domains is something that you had to know a lot about when we had hubs connecting up devices instead of switches. So switches are intelligent layer 2 devices that look at a frame, source and destination MAC address to decide where to route a frame. Hubs are repeaters. Whatever bits come in one port get sent out to all ports. If you had that situation, then we were transmitting what we called half duplex. If you had 10 devices hooked up to a hub, only one could be transmitting at a time. And if 2 of them tried to transmit at the same time, that created a collision. So if we had 10 computers plugged into that hub, we had a collision domain of 10 computers. Now you don't see that anymore because what happens with the switch is they run in full duplex. But 10 megabit Ethernet, 100 megabit Ethernet, and I'd have to double check to see if gigabit Ethernet still supports hubs. I don't think it does. I know 10 megabit and 100 megabit switches could support half duplex hubs. We don't support hubs anymore. So full duplex is auto negotiated when the network card hooks up to this switch. It says I can operate at layer 2, and the switch says I can operate at layer 2, and that means full duplex. So what's full duplex? Well, that's where we've got one set of wires transmitting and a different set of wires receiving. So I can be transmitting a frame at the same time I'm receiving a frame because they're on different wires. That didn't happen on the hub. You would have a collision. So collision domain is how big a group of computers can have collisions. You only have that with hubs. Now the other thing that auto negotiates on switches is speed. There is a way for the PC, like say you have an older PC that only has a 100 megabit card and it's plugged into a switch that can do 1 gigabit. Well, the switch will slow that port down to 100 megabits to operate at the slower speed of the network card. So that is also auto negotiated. So collision domains, you have collision domains when you have a hub, a layer 1 only device, and only one device can be transmitting at a time. The other problem we have with switched networks is broadcast domains. So if this PC or this server sends a broadcast, it gets sent to all of these devices, every single port except for the one it came from. If this server, this computer sends a broadcast, it would be broadcast out every single port of S1 except for where it came from. And since S1 is connected to S2, the broadcast will propagate to S2 and then it will get sent out to all these ports. If you have too many computers, too many layer 2 devices all hooked together, you could have a broadcast that goes to hundreds and hundreds of different devices. And computers periodically send out broadcasts, so you could be starting to bog your network down with lots of broadcasts. If you get too many broadcasts, you can get network congestion, and you'll see this in the animation on 4222. So here we go. Exciting animation. We have a broadcast being sent out to switch 1 and it goes to all the other ports. And that's fine because we only have 5 devices on this switch networks. But when we send it out to switch 1 and switch 1 is connected to switch 2, the broadcast will continue on to switch 2 and be sent to all those devices. So that is a problem. You don't want your broadcast domains to be too big. So how do you alleviate network congestion? Well, so you do not have collision domains, you use switches, and that gives you full duplex and no collisions. If you high port density, large frame buffers so you can store lots of frames, high speed ports, fast internal switching, low cost per port. So I'm not sure how these items alleviate network congestion, at least collisions. They will not eliminate broadcast domains, okay? Oops, I've lost my slide. So all these things, having high capacity on your switches, high port speed, large frame buffers, fast internal switching, those all will help alleviate network congestion. But if you're making your broadcast domains too large, you're generating a lot of traffic on your network, and that will be a problem regardless of these issues. Full duplex with switches, that's what everybody does now. All right, so this activity is kind of tricky because the first thing you got to look at when you do this on 4224 is, are they asking you about a broadcast domain or a collision domain? And remember, these are hubs which do nothing for collision domains, and then switches are the symbol we're used to. So let me go do a few of these. And then as you do these, if you're getting confused, you can always hit the answer button. So let me jump out to 4224. So in this case, it's asking me to draw the shape around each broadcast domain. So since I have hubs and no switches, it doesn't matter. This whole thing is a broadcast domain. Any one of these devices, any one of these PCs sending a broadcast, it will go to everybody. And it says correct. And I could check the answer and it draws a little nicer. Then if I go to button 2, it wants to know what is the broadcast domain of this network. Well, if the router sends a broadcast, it's going to go to everybody. If a PC sends a broadcast, it's going to go to everybody. So I think in this case, we also are hitting everything because we don't have any switches. Okay, so far so good. Now this one we have a switch. The switch will break up collision domains. They're asking about collision domains. So each port of a switch is a collision domain. So that's one collision domain. This is the second collision domain. And then there's a very tiny collision domain with the router and the switch. Let me do a check. Correct. And if I hit the answer button, they draw it so much nicer. So you get the idea. You can go through these, but pay attention to whether they're asking you about a collision domain or a broadcast domain. So collision domain, we've got just a ton of little baby collision domains because switches have full duplex communication. So let's see if I can get these all drawn successfully and see if it likes how I drew it. Yes, correct. And if I hit the answer button, it's so much nicer the way they draw it. But do this exercise right here, 1 through 8. Pay attention to whether they're asking you about collision domains or broadcast domains. If we have a broadcast domain, remember, Switches do nothing to stop broadcast domains. So this right here is one broadcast domain. Routers break up broadcast domains. Switches break up collision domains. Routers break up broadcast domains. And let's go on to the next slide. So on 4312, there is a syntax checker for you to practice and review basic switch configuration. Remember, this makes you type the whole command out and you cannot abbreviate it, but you really need to review and practice switch configuration. And I think I had you do that in an earlier chapter just to get some of the rust out at the beginning of Cisco too. And we did that with our hands-on lab last week. And we are at the end of chapter 4, which is an overview of switched networks. And that does indeed bring us to the ta-da slide. Thanks a lot. See you in the live session and see you on campus.